Hello and welcome to my next presentation on the Sonometer. Hallelujah by the late great Leonard Cohen. I'm not going to play any chords, but the Sonometer does indeed relate to stringed musical instruments. So this is Fez Physics and I'm Bernard Taylor, so let's get moving. Sonometer is a device which allows us to vary the length of the string, the tension in the string, and the thickness or the mass per unit length, as we'll see, of the string, or indeed of the wire. Now, how do these factors affect the frequency? If we increase the length of the string, yeah, we get a lower frequency. If we increase the tension, yeah, a higher frequency. And if we have a thicker wire, as in a double bass, then we get a lower frequency. And of course, this leads on to stringed instruments. Now, I'm going to spare you the sound of me playing the violin, which is about as tuneful as me playing the musical saw. So let's get moving. Here we have our sonometer. The sonometer is essentially a sound box with a string or a wire fixed at one end, going across a number of bridges over this pulley, and we've got masses at the end which give us our tension in our wire. We can measure the frequency of the fundamental note using software such as Audacity, which has a spectrum analyzer capability. So we can vary the tension in the string by adding more masses. We can change the length of the string by moving the position of the movable bridge. And let's suppose we have the length from this point, then to get the fundamental, we'd pluck it in the middle, round about there. But we can, as I say, change the position of this movable bridge, and that would change the length of our string or wire. We can also put in different wires, different strings, some heavier, some lighter, and that would affect the frequency of the note. Typically, as I add down at the bottom, the bridges are made of hard wood. So, sadly, in the current crisis, I don't have access to a sonometer, but I still have my violin. Now, Audacity, I love it. We may have a computer microphone or a laptop with an internal microphone. And what I've done here in plucking, yeah, it wasn't a sonometer. I haven't got access to a sonometer in the current crisis, but I pluck it several times and then I highlight several of these pluckings. And then I go to the analyze box, which gives me my frequency analysis. And look at this, the fundamental is here, and the peak for that fundamental is given. But then we also have various overtones or harmonics. And, you know, this is so easy to do. And in fact, we might ask ourselves, how many plucks could a plucky violin pluck a pluck if a violin plucker could pluck strings? I'll leave that for you to work out. Of course, we need to be careful of safety. The wire might snap under tension and whiplash. Wear safety glasses, put a protective yoke or some kind of cardboard cover over part of the wire, but not touching the wire. If the wire snaps, the masses might fall to the floor. Put some sort of cushioning material on the floor and make sure your feet are out of the way if you value your toes. And here we have one fixed end, the other fixed end, and we've plucked the string in the middle. And of course, this is a standing wave pattern that we've got with a node, and an antinode in the middle. where we're plucking it. Transverse waves travel towards the two ends of the wire, reflect back in opposite directions, and then the superposition of these two reflected waves gives this standing wave with its two nodes and antinode. And let's remember that the antinode is an area of constructive superposition. The two nodes, are an area of destructive superposition. And this is a story that you may well be asked to tell in an exam question. Please remember that the distance from here to here, that's the length of the wire, but that's half a wavelength. So we can imagine that's half a wavelength, and we'd continue on for another half wavelength to get the full wavelength. But L equals lambda over 2, or lambda equals 2 times the length of the wire. So lambda equals 2L. Here we are, as we said a moment ago, using the wave equation, V equals F times lambda, and that leads on to F equals V over 2L. Now, the tension in the wire would remain constant here, so the speed of the transverse wave along the wire would be constant. V is a constant. So what does that tell us as far as equation 1 is concerned? Yeah, it tells us that the frequency is inversely proportional to the length. So the shorter the wire, the higher the frequency. The longer the wire, the lower the frequency. And that's something that we intuitively, I suggest, knew at the beginning of this presentation. Now, you might have had the opportunity to use one of these very long springs on the corridor floor outside your lab to transmit a transverse wave pulse. I love doing this with students. You can increase the tension in the spring by pulling the spring further back, and the speed of the wave pulse, clearly increases. You can do the same sort of thing with a slinky, but these long springs are just much more fun. So, in fact, the relationship between the speed of the wave and the tension is that V is directly proportional to the square root of the tension. I'm not deriving that. So the greater the tension, the faster the speed of the wave. If we have a thicker or heavier string, as we often do in a double bass, for example, then the thicker string or wire has a larger mass per unit length, we say. And the greater the value of the mass per unit length, the lower the speed of the wave. You might think about why that would be the case. In fact, V, the speed, is inversely proportional to the square root of the mass per unit length. And we're not deriving that, we're simply assuming that, and we're calling that equation 4. If we combine equations 3 and 4, then we get equation 5. In fact, the constant of proportionality with SI units here turns out to be 1. Now, let's substitute our value from equation 1, F equals V over 2L. Let's substitute the value for V into here, and we get that F equals 1 over 2L times the square root of T over mu. Now, this equation 5 here is usually given in your formula booklet, your equation booklet, but you should be prepared to derive equation 6, which, as you've seen, is very easily done. Now, what does this equation 6 tell us? It tells us that if we increase the tension, yes, the frequency will increase. Okay, I know there's a square root sign in there. If we increase the length, the frequency decreases. If we increase the mass per unit length, the frequency decreases. And yes, all these relationships were relationships, as I've said, that we sort of intuitively know with stringed instruments. To calculate mu, the mass per unit length, what I would do is simply take my string, measure a length of it, here 0.85 meters, and then put it on a digital balance and find its mass. Of course, we've got to convert to kilograms, and mu is simply the mass in kilograms divided by the length in meters. And here we have a typical value for a string. Now, let's look at equation 6, which we've got over here again. Let's square everything. So then we get f squared equals 1 over 4l squared. Square root bracket goes, so we get t over mu. And if we're plotting a graph of f squared against t, why would we want to do that? Aha. Well, f squared is the y-axis and t is the x-axis, so the gradient is equal to 1 over 4l squared times mu. And if we're doing this as an experiment and we're varying the tension by adding more masses, and for each tension we're getting the frequency squared, and then we should get a straight line graph. From the graph we can work out the gradient. We would assume that we know the length of the wire that's under test. We're keeping that length of wire constant, so we can work out the value for mu. And this is quite a common exam type question. Alternatively, we might have a setup where we're changing the length and keeping the tension constant. So we've got frequency against 1 over L. Why? Well, let's look at equation 6 again. Let's rearrange it slightly. F equals 1 over 2 times the square root of t over mu times 1 over L. So the 1 over L is our x, the frequency is our y, and the gradient m will equal 1 over 2 times the square root of t over mu. So again, if we know the gradient from plotting our graph, we know the tension, we're keeping that constant from the number of masses attached over the pulley, we can again find a value for mu. So here's a sort of past exam question. Let's read it through. A student carries out an experiment using a guitar string. She investigates the effect of varying the tension in the guitar string on the frequency of sound produced when the string is plucked. Describe a method of varying and measuring the tension in the string. Well, we could have drawn a sonometer and shown that the string was actually a guitar string, or another way of doing it, perfectly adequate, is to show a pulley is the string leading to these masses, and we've got the other end of the string which is clamped between two wooden blocks and a G clamp over here. How are we going to vary the tension? Well, we know that T equals mg, so change m and measure T according to this equation. Yes, drawing the diagram does save a little bit of explanation, but writing down a few words in explanation is vital. So what does the student now do? Well, the student records this data and we can see we've got tension, frequency, and frequency squared. Oh, we've got frequency squared along the y-axis and tension along the x-axis. And we've got one value that needs to be calculated here. And we've done that here. We've plotted a graph, line of best fit. And yes, I've anticipated the next part of this question by calculating the gradient. Ooh, look at those units there for the gradient. Are they right? I hope so. So the student reads that the guitar strings have a mass per unit length of between 0.4 times 10 to the minus 3 kilograms per meter and 7 times 10 to the minus 3 kilograms per meter. Does the guitar string used lie within this range. We've got the length of the string, 0.4 meters. So yes, you know what we're going to do. V equals the square root of T over mu. We know the wave equation, and we know then that V equals F times 2L. Why 2L? Well, we're dealing with the fundamental, so lambda over 2 equals L, lambda equals 2L. So we've got this equation for the speed, we've got this equation for the speed. Let's equate the two. F equals 1 over 2L times root T over mu. It's looking very familiar. And F squared equals all this lot. Okay, the gradient of the graph certainly equals 1 over 4L squared mu. Let's put in the numbers. The gradient that I established just a moment ago was this, 255. We've got 4. We've got the length of the string squared, and we've got mu. So we get a value for mu, which works out to be 6.1 times 10 to the minus 3 kilograms per meter. Does it lie within the range? Yes, of course it does. But say that in an exam question. Now, as we approach the end, I'd like to just talk about a related experiment. And at A, we've got, between A and B, we've got a string. Typically, when I show this in a lab, I would use an elastic cord, which works very well. A is attached to a vibration generator, which in turn is attached to a signal generator, so we can supply different frequencies. And this point would move up and down slightly. B, point B, is fixed, and we would have a constant tension in the string. When we adjust the signal generator, connected to the vibration generator, at 15 Hertz in this case, the length of the string is 2 meters. In this case, we get the fundamental at 15 Hertz. And of course, from here to here is half a wavelength. So the full wavelength will be twice that. So lambda equals 4 meters. We can increase the frequency. Yes, we do increase the frequency. And we get the first overtone or the second harmonic when we see this kind of pattern. And it's a standing wave pattern, and you know the story to tell about standing waves. We've already gone over that. And this happens at a frequency of 30 Hertz. And in this case, that's lambda. So lambda equals 2 meters. We can increase the frequency a little bit more, and we get the second harmonic, or as it's sometimes known, the second overtone, or the third harmonic. And in this case, it happens at 45 Hertz, and there's one wavelength and another half wavelength. So 3 over 2 lambda is 2 meters, and that leads to lambda is 1.33 meters. So this is just a reminder about fundamental and about harmonics. And a rather neat demonstration experiment, which I love to set up on open evenings. Now, what's this? A couple of years ago, I went to visit the Wordsworth Museum next to Dove Cottage in the village of Grasmere in the Lake District. And one of the exhibits I saw was this Aeolian Harp, and I got very curious. The Aeolian Harp would have been put in on a window sill, and the wind blowing would create pleasing sounds. What is this Aeolian Harp? Essentially, it's a sound box, and you can see this has the wire strings. The tension in the strings can be attached. These pins are known as zither pins, and you can have a special kind of tightener, or you can use a pair of pliers to change the frequency. And here I made it so that the frequency in each string was different. And when the wind blows across, in this case, moving across in that direction, we get some pleasing sounds. Aeolus was the Greek god of the wind. Now, there are various designs of Aeolian harp, and this is something that you might like to try as a project. I've seen Aeolian harps, essentially a stretch wire that has been 2 or 3 meters in length. And when I was a lad, quite a few years ago, I remember you used to be able to hear telephone wires making sounds in a strong wind. Well, to let you into a secret here, the sound produced by my Aeolian harp is quite quiet, really. And I've toyed with the idea of putting a pickup on the box somewhere and amplifying the sound. And it would be nice, I think, to do that. So, and can I just say, well, maybe we'll have an exam question on the Aeolian harp one day. We shall see. So, this has been Fez Physics. Stay tuned for my next Fez Physics video. And if you are interested in online tuition, then please do contact me. But whatever you're doing, keep working, stay active. Thank you very much.